Hi, my name is Dean Sessions, and I'm the author of The Universal Model, a New Millennial Science. Today we have a fundamental question to talk about, and it's an important question. It is, where does salt come from? Salt is an important component of all of our lives. Matter of fact, we have this type of salt, NaCl, in our dining rooms and by our tables where we eat, and it's a common thing that all living things have to have every day. We have to have salt in our diets. So what we want to talk about is a very important, interesting question. What is the most abundant mineral earth on the entire surface of the earth? This question over here, you can see in the green words, is a very, very important question. And this most abundant mineral is called the salt mystery. We can see here in this diagram right here that if this first part, if the salt in the sea could be removed and spread evenly over the entire Earth's land surface, it would form a layer more than 500 feet thick, about the height of a 40-story office building. Now, what's important with this is actually the answer to a question over here in the salt mystery is, where does all the salt come from in the oceans? Well, if we go to the USGS, which is a geological survey, we find that salt in the ocean comes from rocks on land. That's their quote. All the salt out of the ocean is supposed to come from erosion from the rocks on the land. So in this diagram here, we can see San Francisco, 500 feet thick, would be covering most of the buildings in downtown San Francisco. And we can see down here on the bridge. This really comes into a better perspective when we look over here and we see that, however, if the average thickness of the land surface is only 410 feet, that's 125 meters, how can 500 feet, 152 meters, of salt come from these 410 feet? So we have other geological researchers that went ahead and calculated, if we take all the land on all the continents and we flatten it down, how thick is that land? Well, there's a lot of low-lying areas, and so the mountains all actually flat down to about 410 feet. So now we have a tremendously important question. How does 500 feet of salt that came out of the oceans come from 410 feet of this land? It doesn't work. And another important aspect of this is, when we take salt water, if we put about 1 liter inside a jar like this and evaporate it, you get something like this. Okay? This is regular seawater that's evaporated. The problem with this, though, is that when seawater evaporates, it's not just one single salt. And this happens to be what we find in our salt deposits. So let's go ahead and see if we can find that here. Let's go ahead first off and take a cruise here just down to the next page. This is page 133 of the Universal Model, the first volume, by the way. That's what we're looking at. And here we see table 1. Down here on the right-hand side, we see that these are the elemental composition of the igneous rocks. So everything that we have on the earth today is supposed to have come from the igneous rocks. And if we look here, we can tell that oxygen is the first one. That's because that O is in a lot of rocks. Silicon dioxide, which is quartz, SiO2, that's why it's the most prevalent. Then aluminum, iron. All the remaining ones are very minimal. Matter of fact, sodium is less than 3%. So the first question we have to ask here is, where is the chlorine? Remember, sodium chloride, that's what the salt is that we use at our dinner table, is NaCl. Where's the chlorine in this chart? There isn't any. And like it says down here in the bottom, the table shows the percentage of the elements contained in the igneous rocks according to Bowen. Sodium chloride is the most abundant mineral on the entire surface of the earth, which includes the oceans. However, if all elements, including salt, came from igneous rocks, why is there no chlorine in the igneous rocks? So this is a very important question that we don't find answered from millennial science. From modern science, but millennial science can explain it. Let's go ahead and go to the answer. We're going to pop over here to chapter 8. So this chapter 8 is subchapter 8.9, the salt mark, and this is where we have the answer to the question of what is the origin of salt, as you can see right here. This is a geologist. Woolnow was one of the few geologists that actually understood that the processes today don't work in making the salt. And this is why it's been such a mystery in geology. He stated right here, in no instance were conditions encountered which could conceivably have produced any of the major primary salt deposits of the geological past. Some circumstances or set of circumstances entirely lacking under the present day conditions must have been operative when such major salt deposits were generated. So what is he talking about here? Well, to understand that, let's look at, we're going to go here to the next page, I guess. Yes, let's do that. So we're going to go down here and look at, this is a salt mine in Poland. Beautiful. They carved all the inside out there. It's really pretty. Matter of fact, I have a piece of salt here from Russia. This is a Russian salt mine. Okay. And some of the salt that we find, and that one had a little pinkish color in it. We're going to talk about that here in just a second, because this is really a key right here at the top. In the green letters, the key to the origin of salt. It's really simple. Salt is a biogenic mineral. This means it formed from microbes. Yes, microbes. Microbes are a really important part of the universal flood. This was an event that took place 4,362 years ago. This is explained in this chapter we're working on, where we're at here right now. And it's very descriptive, where we go in and go into a lot of detail, showing this is a salt mine here in Michigan, showing how much of the salt, this actually is under most of the state there. Several of the states have huge geological deposits, and we're going to talk about that here in just a second. But first, let's go to the acid-base biosalt origin. And what this is a simple explanation of how salt comes from microbes. This very first formula is the only one we'll look at right now. HCl plus NaOH equals NaCl. This is your table salt and water. So this is actually where salt comes from. We don't have Na and Cl in nature by themselves. Very important point. You don't go up in the mountains and just find sodium or chlorine. Chlorine kills all living things, and sodium doesn't exist in nature. So these two things don't exist by themselves. What we find in nature is when you have certain microbes that are, they're byproducts. When they pass away and what's left over is hydrochloric acid, that's what this is, and sodium hydroxide, the base. These two things come from microbes when they die. And when we take these two things and put them together, they're two clear liquids, and when they're mixed together, they give us this H2O and NaCl. Usually the water is not perfectly clear, so there's going to be several kinds of salts made. But in the case of salts, and we explain here in this chapter, that depending on the pH level and the temperature of the water and also the pressure that they're under, we find an environment that separates the liquids. And so now we're going to, besides asking the question, what is the most abundant mineral on the entire surface of the earth, which is salt, we want to go back to and ask another question here. This question is going to be really common if we want to talk about what the largest rock in the world is. The largest rock in the world is actually what we see here on the right-hand side here. It's called a salt dome, or we'll explain why in a second, actually a salt plug. And keep in mind, this is very, very important. When I would ask geologists, what the largest rock in the world is, you'd think it's part of their profession. They would understand this, but it's not what they're not taught about in school, and so it's not commonly taught that the salt is the largest rock. This particular one, they're actually over 7 miles deep. The largest mountain in the world is 5 miles high, Mount Everest. So this is actually bigger than the biggest mountain in the world, this 7-mile deep salt plugs or salt domes. You can see here that this diagram shows the vertical pillar of salt and some oil deposits found up at the top. When in Texas and the Gulf Coast, this is where they find a lot of this salt domes, and oil deposits are connected to them. So the oil they know comes from microbes, and we describe that also in the chapter we're working in, the origin of oil and how it's made. It's all made in the same process. But these salt domes, what's going on down here at the bottom, this is a theoretical thing. They thought the salt comes from evaporation. And that's the problem, is the salt domes are not coming from evaporation. They're actually coming from microbes out of a entirely different process. Let's go ahead and show you. Here's another example of these salt domes. This is a chunk of salt. We normally don't see this this large of a piece of salt. It's very common, obviously, when you go to salt domes, because the entire mine is full of this salt. Let's go ahead, and we're going to go back here and look at a salt dome again in this particular chapter 8, and we're going to pop down here to page 606. So this is chapter 8 again, right here, and this is the Big Hill Salt Dome. Instead of the salt on the bottom, you notice how that other diagram, it went down like this, flat on the bottom like that? Well, instead of that happening, what you see is actually a diatreme. This comes down to a point, and this is very important. We're looking under the ground right now. This is halite, which is NaCl, that's your table salt. And hydrite up here at the very top is a separate, they call it a cap rock, and it's also a salt. It's gypsum that doesn't have water in it. And what you see here, these are so large that the United States Petroleum Reserve for 2 years is stored inside these salt domes. That's what these blue lines are up and down here. They actually drill a mile down into these salt domes, and they pump water down in there, and the water comes out salty, and it dissolves and makes these large caverns that they fill full of gasoline and petroleum. And this is where our oil products are stored. So it kind of gives you an idea. 2-year supply. Right now we have about a 2-week supply in all the gas tanks of all the cars in the United States. There's a lot of cars. Imagine all of those just 2 weeks. Imagine having a 2-year supply of all those tanks of gasoline inside on these salt domes. So that gives you an idea of how massive they are. Notice down here it says there's no evidence showing that there is a salt bed below the salt plug. And this is because we're going to show you right now how these salt plugs were made. Okay. Matter of fact, let's read right here at the bottom. The Big Hill Salt Dome of Texas, USA is a typical salt diatreme. We're going to talk about that word. It's a very important word here in just a second. That should more correctly be called a salt plug, because the diatreme became plugged with salt after pressure and temperature changed during its hyperthermal growth period. This hypertherm is a new term that we use in the universal model, and it helps us understand that minerals are made both under temperature and under pressure. There is not a term right now in physics or chemistry that describes the way rocks are made, and we actually make rocks here in the universal model, and the way we do that is under pressure and temperature. And once you can make a rock, well, now you can describe it a lot better. So we're going to show you right now how rocks are actually made. We're going to go down to the next page here, page 608 actually. And right here in the bottom right-hand corner of 608, we're going to see a very important mound. This is called the Tag Hyperthermal Mound. And this mound is actually, like it says in the figure description down here, 3,700 meters below, or 2.3 miles below the surface of the ocean. So it has this much water over the top of it. And Tag is a mound that has 338 degrees water coming right out of the top of it here. The reason we can show this diagram and the cross section of it is because we've actually drilled down to this mound. This is on the bottom of the ocean. Think about that just for a minute. This is the bottom of the ocean, and there's hot stuff coming out here. Matter of fact, I'm going to show you a real live one. We'll come right back to this. I'm going to show you a live one, what this looks like here. I think there's one right down here. Okay, I just found it. It's actually, well, I'll show you. That's a good picture we're looking at right there. That's Salton Sea salt. Here's a real live picture that I brought one with me from Southern California. This is what NaCl looks like. It's actually little square crystal shapes. Okay, and this is important because salt, when it evaporates, you get all the salts that come out of the ocean, and there's several of them. There's like 5 of them. But the problem that we have is these salt deposits, what we're talking about here, these salt domes, are actually, like this right here is over 99% pure salt, NaCl salt. So this poses a real problem when we try to understand how we could have these massive salt deposits that aren't made out of this. This has all 5 salts of it together. There's only 1 salt here. And how does that happen? How do we get these 7-mile deep, huge salt domes? Well, this is how it happens. Let's go ahead and pop back over here, page 599. So I'm going to come down here real quick, right here. So this is a black smoker, and there's also white smokers that are on the bottom of the ocean floor. And this is a picture of an actual one releasing its fluids. Okay? And the discovery of hot smokers on the seafloor is completely changing the way science looks at the mineral crystallization. We can observe salt formation in process that reveals how geological salts and ore deposits were formed. We're talking not only about salts here, but this actually comes back to all the ores. Now, the ores are extremely important because you and I right now would not be communicating. You wouldn't be able to see this on the internet unless we had copper wires running through homes and the other metals that we use in our phone and modern technology. All those metals come from ores that came out of this process. So this is fundamental, and we have to understand ores are not forming today. You don't go anywhere in the world and finding ores just happening, except in these very specific locations like this on the bottom of the ocean. And so we're going to go back now down here to this 608 page. And on the bottom of 608, we're going to bring up the tag mound again. We want to finish by explaining what we find on the bottom of the ocean. When we are in the right pressure under several miles of water and we are at the right temperature, 338 degrees Celsius is way below the melting temperature of a rock. You need about 1700 degrees Celsius to melt quartz. Yet right here you can see quartz is being formed. That's right. It's not melted, it's crystallizing out of the water. And same with anhydrite, same with pyrite. Pyrite is the fool's gold that's found all over the earth in sedimentary materials. The small little bits of fool's gold. Pyrite is an extremely important part of actually We demonstrate in this chapter that it came from microbes, and we also have basalt down here. So basalt, quartz, these are some of the most abundant minerals on the entire surface of the earth, as far as underneath the oceans and also on top of the continents. And the way these all formed, we're looking at right now in the TAG hyperthermal mound. So this is a important understanding for us to grasp how salt is made. First off, it's the most abundant mineral on the entire surface of the earth. For just a moment, let's ask a question. If we go to the moon, how much salt do we find there? It's the most abundant on the earth, so the moon and the earth are supposed to be made together a long time ago in some accretion theory process. Well, how much salt do we find on the moon? Interestingly, 0. We didn't find any when the astronauts went there and brought hundreds and hundreds of pounds back, and we've analyzed every grain of it. There's no salt on the moon. Why is this? Well, the answer is really simple. Salt comes from microbes, and the microbes have to be formed under pressure and the right temperature, and this happened on the earth several thousand years ago when the entire earth was covered with water in the universal flood. This is an exciting new concept to understand in the universal model, is that there was actually a universal flood that explains how all the minerals were formed in the sedimentary process of the earth. These will come up in another video. We'll do it another time. I hope you've been excited and happy to learn more about the origin of salt and where salt comes from today. And until the next time, we'll see you again at theuniversalmodel.com. Thank you.